Hey everybody, and welcome back to Linear Algebra Online. So today, the plan is to talk about a very important topic called span. Span is very directly related to linear combinations, which there was a video on way long ago at the beginning of the year. And to kind of just remind you what this is all about, I thought we'd start with this example. So the question is the vector 1, 2, 3 a linear combination of 1, 0, 3 and -1, 1, -3? So I think a picture can actually kind of help here. So if you have, let's just say this is vector v, and this is like w. A linear combination, and this is like, I don't know, u. So the idea is like maybe we can go v, and then maybe like this is 2w or something. And with some sort of combination of those, is there a way to get u? So u could maybe be here, v plus 2w. Or maybe u is going to be like -v minus 7/3 e of w, because why not, right? So if I set this up, the idea is like, can you take some amount of 1, 0, 3 and add to it some amount beta of -1, 1, -3? And can that be 1, 2, 3? And you could guess and check. That's what I say here with the brute force thing. But it is definitely not the way to go. You can actually just turn this problem into a matrix is actually the best way to do it. So the idea here is like if you think like 1 on 1, let's just take this, 3 plus z equals, I don't know, -1, -1, -1, and then 1, 1, 2. So we're not used to thinking of a system of equations in a matrix kind of written out this way, but you actually can take something of like this structure and just put it directly into a matrix. So you could think of this as, the first line in the matrix could be x, 1, -1, -1, 1. Basically the plane x minus y minus z equals 1. So this can turn into like 1, -1, -1, 1, 1, 2, -1, 1, 1, 3, -1, 2. And so basically, if you ever want to know questions like this, you can actually form a matrix and then just see if there's a solution of it. And if you get something after you like RREF it that is solvable, then you will know like these two things. And if you do this one, I'm actually going to erase this because I need more room here. So if I do this one, I'm going to get 1, -1, 1, 0, 1, 2, 3, -3, 3. And if you just RREF, you get 1, 0, 3, 0, 1, 2, 0, 0, 0. So what this says is you basically need, this says like alpha would be 3 and beta would be 2, right? So you can check it. If you do 3 of the 1, 0, 3 vector and you add to it 2 of the -1, 1, 3 or -3 vector, you actually should get 1, 2, 3. But solving like a linear combination problem like this is actually the same as just solving like a matrix problem. You're just not kind of used to thinking this structure giving you a matrix. And that's actually why I like the structure of vector forms for lines and planes so much, because they have like a real analogous structure to a matrix like this. So like I was saying, plan for today is really to talk about span, but I'm actually going to let this guy talk about span much more because it's something that you really can just see in a video. And we're going to kind of just go through some examples to kind of get a sense of the span of different sets of vectors. But this video is something that I would definitely want you to watch really before you watch the rest of this video. And he just does a great job in here, basically showing you visually, like the part I can't do, just what span is, what linear combinations are. And there's this part about basis vectors too, and we won't talk about basis vectors actually for a little while, but it's good to still see it now because it's just going to come back soon. So the definition of span in your book is given down here. It is a set, or it's based on like a set of vectors, I should say. And the idea is, honestly, almost sort of similar to like the idea of the power set, that set of subsets. So what you're getting when you look at the span is basically the set of all linear combinations of your vectors in this set. So you sort of have like one set to work off of, and then you start thinking, how many different linear combinations can I form? You know, I could have formed, like I think I did like, you know, one of these plus two of these was my first one, I was saying, like first linear combination. But you could also take e of these and pi of these, you know, and you can get another vector. But you basically take all possible combos of the vectors in this set, and that is what represents the span of the vectors. And we write it, span, and then parentheses, of the vectors. Or like if we've defined the set of the vectors a certain way, we can just simplify this and put in an S there, basically. And this is kind of another little part of the definition, that if the span of the set of vectors in Rn actually fully spans Rn, then we call it a spanning set for Rn. So this video is going to make a lot of this definition, I think, make a ton more sense. So I'm assuming basically at this point that you've watched this. So when I go on and do these examples, it'll make some more sense. So the first example here, I just want to prove, really just like computationally, that these two vectors span R2. And basically, the idea is, if I have like some X amount of 4, 5, and I add to it some Y amount of 5, 8, I just want to show that I can get any single vector AB, like for all AB in like the reals. Like I can get any vector I possibly want. If I can do this, right, if I can make any 2D vector from some sort of combination of this, then these two form a spanning set for R2, is the idea. And a lot of vectors form, a lot of 2D, getting lost in my words, a lot of sets of 2D vectors span R2, because like intuitively all it's saying is like, here's some 2D vector, here's a different 2D vector, and that would form, you know, some sort of two-dimensional plane that's just analogous to getting me all of R2. Really the only way it's not going to happen is if you have one and then you just have overlaid like a linear, a scalar, of that first one, then all you're going to be able to span is like a line. You wouldn't be able to get out of that and get like the 2D part. You would only have 1D. So that's like the intuition. But the way you actually prove it is basically what I'll go through here. So I'm going to make a matrix, kind of like I was talking about previously. So 4, 5A, 5, 8B, and I'm going to RREF the thing. And if you do that, I just did it before. I did it and got 8A over 7 minus 5B over 7. And then I got 0, 1, and then negative of 5A minus 4B over 7. Because sure, why not? So, honestly, it's kind of maybe not obvious right off the bat, but this actually basically would prove it, because what this is saying is to get A and B, just let this thing right here says, like, let x equal 8a minus 5b over 7, and let y equal the negative of 5a minus 4b over 7. And so the idea is, like, I can now get any vector ab if I just, I have a formula, I guess is how I'm thinking of it. Like, say I want the ab vector to be just 0, 1. So a is 1, b is, a is 0, b is 1. Then I have my formula here. So I would get, let's say I'd get negative 5/7 better be x. And I would get math 4/7 is y. Yes, I think I did that right. So that's just saying if I take this many of 4, I take, let's be specific here, negative 5/7 of this, and I take 4/7 of this vector 5, 8, I should be able to build 0, 1. That's the idea. And you could just go through and do that, like for, different a's and b's, and you have your little formula. The only way this would basically not work is if you get some a or b on the bottom where the 7 is. Because then it's something undefined, right? Like, because you maybe could get, like, you still want a to be 0, but if you have a 0 on the bottom, then, there's certain vectors that would be unattainable by this, a linear combination of these vectors. So this is just a really important concept here, and there's actually a theorem in the book. Actually, I'm going to look it up. I have the book right here. So if you look at theorem number 2.8, it basically sums up this example, but they use words, and I think it's almost easier to see this with numbers. So the question is, if you have the vectors 4, 5, 5, 8 from before, and then you stick in pi and e, the span of that, would that still equal R2? And hopefully it's not too hard to think about, but yes, definitely. The idea is, like, if 2 vectors did it, right, then 3 should. If you have a picture, say this is 4 and this is 5, that vector, and then we got, so this is my 4, 5, this is my 5, 8. So I'm going to say 5, 8 is like, so this is 5, and this is maybe 8, like that. So these vectors are not scalars of each other, so they're actually going to be able to give you all of R2, like we just literally showed that over here. And so if I stick in a third vector, pi e, pi e is like, I'm going to say it's about right there, and then it's about right there. This vector doesn't even need to be stuck in because R2 was already attainable by the other 2, but it's still going to span, R2 if you stick in more. It doesn't really need to be there. That's the whole point. But it's not going to stop it from happening, basically. So the theorem in the book says that, like, any, it's a really short one so I can write it, any set of m vectors in Rn is linearly, how do I spell this word? Linearly dependent if m is bigger than n. Now, it might not seem like we haven't really defined this word yet. We're going to do that soon, actually next class. But this actually is very directly related to this. So you have in R2, right, we have 3 vectors. So this satisfies this definition. 3 is more than 2, right? And the idea is basically this, like yellow vector, we can think, is basically linearly, there's something in here that can be written in terms of the other ones. You don't need pi and e to be thrown in. It can depend on the other 2, basically. Now, if you take away 2, though, you're definitely going to only span the line that relates to the direction vector of that vector. You're not going to be able to get the entire R2 space. So you'll see more about this, a lot more about this in a whole nother video, but actually this kind of problem is conceptually why this theorem even works. Maybe I should also add, if you like equations, you can also just think about it this way. We already found x and y that we can add together and get any sort of like AB. So another way you can kind of think about this is I could always just add 0 of pi and e, and that still works, right? If I tack this on to this thing that I had already solved, then I just basically add a 0. It's fine to do that. And so it still spans it. Like, it's just the linear combination is like some amount of this, and always 0 of that one. And you can always get any vector. All right. So I just want to do one more example. Find the span of these two vectors. And first I want to start with really conceptual understanding here. So this is really where I want to start. So could this span R3? I mean, you can even draw it. It's not super hard vectors to draw. So 1, 2, 3, 4, 1, 2, 3, 4, 4, and then yeah, we'll go dotted down there, dotted over here, dotted over here, and then we'll go down a little bit. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. It's not going to be a perfect picture, but so this vector would look like going out 1 in x, nothing in the y, and then 3 up. So I'm going to say it's like kind of like that. And then we'll do purple. The other one is -1 in the x, 1 in the y, and then down 3. So it's kind of like dropping down like that. Very hard to see, but the point is, you could connect, you can think of these two as, spanning basically a plane. And actually, I'm going to try and redraw this a little bit more, like over here. So they can define the plane like this, right? That would go through the origin. But it's very much a two-dimensional plane and not a three-dimensional space. You need 3 vectors to span R3, just like we needed 2 or more to span R2. You're only going to get a line with 1 vector, so you need 2 there to get 2, and you're going to need 3 to get 3. So like geometrically speaking, this is just a plane in R3, okay? And the way we actually find the span is we literally just say it is like the set of all like x, y, z, which would equal like some scalar of the first one plus some scalar of the second one. And, this right here is just a plane that goes through the origin, which I was going to try to draw here, but I think I failed miserably, but that's okay. But this has, no like point in here. It's just the point 0, 0, 0, and then I add these to it. And the idea is like, since these vectors, this yellow and this purple one can move around, like I could take this vector and move it out, and it could cut through a plane over here. It could cut through a plane that's like back there. But typically we think of the simplest one, which would be like the one through the origin. We don't need to stick that point in there. And this is usually actually like how we write it. It's like we would say the span is the set of all points x, y that satisfy this. So I can actually make it like a little bit better. I could add little set brackets, and I could do, this is probably a little more formal. So the set of all x, y such that and then you have like squiggly brackets over here. That would be the span of these two vectors. Okay, I want to do this better because my OCD doesn't like that. Okay, so there we go. So span is the set, right? So it's the set of all the linear combinations of the vectors, and so in this case, it's the set of all vectors like x, y, z, such that, that's what the bar means, x, y, z equals, has this structure of this plane.